That is good.
What are the classes like? I think it's one of the what were the classes like? Like teachers, they really are very open to talk about the side. Like
Yes, let's go.
Which is why seeing this. And we tried, hey, this is about a teacher's time. So this like this can be really hard to write. These are really
Did you win it?
focus
Top one.
on your success.
I was Hey, you. Yeah.
Hi, good morning, everybody. This is about time to start. I'm going to jump right in. Continuing with that section 1.3, there's a problem I want to show you. It's a little bit tricky, at least it looks tricky. It's number 2, section 1.3. In number 2, section 1.3, they got a graph. It's a semicircle, the upper part of the circle. They have some numbers on there. It's up here to 2.5. We got here to 5. And they tell us the equation is y equals square root of x minus x squared. So that's the equation of this graph. And then also there's another graph on there. -3, 8, and then -3, -5.5. It doesn't look great. Let's spread this out a little bit. That looks a little better. The idea is this is the equation for this graph. Here's this other graph that's extremely similar to that one. In fact, the only difference is there's been some transformations, it's shifted, reflected, and some stuff like that. The goal is to get the equation of this one by modifying the equation of this one. There's quite a few transformations happening. to get from here to here. I'm gonna try to show them one at a time. If I take this graph and I just move it to the left, where it's, instead of going from 0 to 5, it goes from -8 to -3. Look like that. Now notice that's the origin, x is 0, out to 5, so 5 units all the way across. It's still 5 units all the way across, so it's just a shift. There's no compression or anything like that. So that's just a horizontal shift left 8 units, like 8 altogether. Because this edge was at 0, we're at the -8, 8 units that way. This one was at 5, now it's at -3, 8 units. So 8 units to the left. So the horizontal shift to the left comes from the x being replaced by an x plus 8. Because if I have a number being added or subtracted to the x, that does left or right. Adding is left, subtracting is right. So it's left 8, so I need an x plus 8 wherever there was an x. I got x in there twice, so wherever there's an x, I'm going to put an x plus 8 now. So the equation for this one, not the answer to the question, x plus 8 minus x plus 8 squared. Again, I just put an x plus 8 wherever there was an x. You don't have to multiply anything out or anything. I mean, you could distribute the 5, but it's just unnecessary work. Anyway, what next? The final graph's upside down. It's flipped. So I'm going to take this one and reflect it. I'm going to flip it. If I do that, I don't have another color here. Okay. I'm going to use a black one. I don't like the black one because it doesn't erase very well. But if I take this orange one now and I flip it, not a great job, but you understand, I think. I just take this and flip it. Of course, it looks a lot taller there. It's supposed to be the same height. That's a reflection about the x-axis. Reflections come from negative signs. Reflections about the x-axis are taking the y values and changing them from positive to negative. So the y value is now going to be negative what it was before. So the equation here simply put a negative sign. So for this one, y equals negative 5x plus 8. And 6 plus 8 squared. Now also notice, when I flip it upside down, the top is at 2.5. So when I flip it down, it's at negative 2.5. For this upside down semicircle, it's going from y being 0 down to negative 2.5. So now I'm going to take it and shift it down, match up with this green one, the final one. I've got to shift it down 3 units. Notice the top of the semicircle was at 0. If I shift it down 3, it's going to be at negative 3. Matches up. If I take this, it's at negative 2.5. Shift it down 3, now it's going to be at negative 5. I need to take this and shift it down 3. A vertical shift down 3. So for vertical shifts, all you got to do is add or subtract the next number at the very end of the equation. I just need to tap on a minus 3 at the end of this if you get it to go down 3 units. So the final equation is y equals negative square root 5x plus 8 minus x plus 8 squared, and then minus 3. With that extra -3 to get it down 3 units. Now it's matching up with that final graph. So there are 3 transformations altogether. Again, I don't have to multiply it out or anything. I mean, you could, but it's just unnecessary work. Could distribute to 5. I could do the formal method here, but unnecessary. You can just type it in the WebAssign like this. If you do multiply it out, WebAssign's pretty good about that. It will still count it right. There are other ways to enter the equation, and WebAssign's really good at situations like that. But anyway, I wanted to show you that one. It's kind of tricky one. Anyway, this section 1.3 deals with new functions from old functions. That's the title of the section. And the main thing it deals with is transformations. That problem. But it's not the only way to create new functions out of old functions. Another way to do it that's used a lot is called composition. Composition of functions. The idea of composition of functions, instead of just shifting a function, we take 2 functions or more and combine them in a certain way. And here's the definition. The symbol looks like this. F composed with G. That's how you would read that. It looks like a little hollow dot. But it's a way of taking 2 functions and combining them to make this new function. This way of combining them is called the composition. But the formula is, for composition, f of g of x. So what I wrote down here is really nothing but a bunch of notation, symbols, but it is telling you a definition. It's telling you how to create a new function with composition from 2 other functions. And the way you do that is you plug one into the other. You take one whole function, plug it into the other. And the way I wrote it here, we take the g function, whatever formula it has, plug it in for the x into the f function. For example, a good one here in the homework, number 5. Four minus 5x. 4 minus 5x. So suppose you got this original function f of x 4 minus 5x, and you got this other function g of x cosine of x. Part A wants us to figure out the formula for the composition f composed with g of x. Here we got these 2 individual functions. We're going to make a new function from the result of the composition of these 2. The definition says it's f of g of x. So we take the g of x, plug it into the f of x. Take the formula for the g of x, plug it into the formula for f of x. The way I remember this, because it's, in my opinion, easy to get backwards, is you think about what you would normally do with a function plugging in numbers. If you got a number here like 3, you plug it into the function right next to it. So in this situation with composition, you take what's closest to the x, plug it into what's furthest from the x. So I take the g function, plug it into that function. So I'm just going to take this cosine of x, put it in where there was an x in that one. So 4 minus 5 times cosine of x. Just put the cosine of x right there. Take the g, put it in for the x in the other one. That's all there is to it. There's the formula. But they do also ask for the domain. Now the domain, in some situations, can be kind of complicated. Because the idea is if you're plugging in numbers for the x, that's what domain is, all the numbers that you can plug in. You got to worry about plugging into the g function and then taking the result of that and plugging into the f function. But for this particular one, and is often the case, it's not that complicated because for cosine, the domain's everything. You can plug in any number in the cosine and you'd be able to do the calculation. And then what you get, we could plug in there because the domain for this function also is everything. We're not going to have any problems like trying to divide by 0 or square root of a negative if I plug into this formula. So no matter what I get here, I'm going to be able to plug it in there. So the domain by default is everything. So it's all real numbers. Negative infinity to positive infinity. Anyway, there's a part B. Also, they want us to do the same thing, but the other way around. G composed with F. So it's the other way around, but the main idea is the same. Take one function, plug it into the other, but this time it's G of F of X. I take the closer function, F, plug it into the one that's further out, the G. So this time, I write my individual function down here again. 4 minus 5x cosine of x. This time I'm going to take the F function. I'm going to take a formula for the F function. And I'm going to put it in to the G function where there was an x. So I'm going to take 4 minus 5x, put it right there. G composed with F of x is cosine of 4 minus 5x. So there's the formula for the composition that way. I did the exact same thing, but just the other way around. Put one function, plugged it into the other. Just different directions for these two parts. Same thing here though, domain. Domain for F is everything. I can plug in any number into this formula and I'd be able to do the calculation. Likewise, when I get a result, no matter what I get, I'll be able to plug in the cosine. Domain for cosines, all real numbers as well. So default domain for the composition is all real numbers as well. There are a couple more parts too that kind of odd. Number for part C, once F composed with F. F composed with F. F composed with F. So I need to take the F function, plug it into the F function. The F function has the formula 4 minus x. Because I'm going to take that function, plug it into the F function, I'm actually just going to write it down twice. It's easier to visualize. So I'm going to take the F function, plug into the F function. I'm going to take this formula for the F function, plug it in for x in the other F function. So where there was an x in, I'm going to take the 4 minus 5x, put it right there. 4 minus 5, 4 minus 5x. Again, just took the 4 minus 5x. Now for those last two here, I couldn't really simplify or anything. This one I can, and I should. So I'm going to simplify this first, distribute the -5. I got -5 in front of the parentheses there, so I distribute that. Got 4 up top. -5 times 4 is -20. And then -5 times -5x is positive 25x. 4 minus 20, -16. So 25x. So there's the formula for F composed with F again of x. Main, same thing, negative infinity positive. So I can plug in any number here. And then once I get that number, then I could plug it in here. Wouldn't have any trouble with the calculator. Last part, G composed with G. That means G of x. Take the G function, plug it into the G function. So the G function has a formula, cosine of x. Since I'm taking G and plugging it into G again, I'm going to write it down twice. And just make it easier to visualize. So I'm going to take the G function, plug it in for the x and the other two. So I have cosine of x. Cosine of the cosine of x. Can't simplify that, I think. So leave it like that. Domain again is all real numbers. So I could plug in anything for cosine. And then when I get there, I'd be able to plug it into the other cosine. So negative infinity, positive infinity as well. I do want to point out something about this though, just with notation. This means the cosine of the cosine. So there's a cosine inside the other cosine. That is different than this. That means cosine squared. That means cosine times cosine. I should be careful there. I should say cosine of x times cosine of x, which is different. That means I'm taking a cosine of x times another cosine of x. This means I got the cosine of, and what's inside that cosine is another cosine. And by the way, you're probably familiar with this. When we have a trig function squared like this, we write it here as opposed to the outside. Because if you write it on the outside, then there could be some confusion. If I write it like that, the confusion could be, is it the x that's being squared or the whole cosine that's being squared? And if you use parentheses, then there's no confusion. Did this, there's no confusion. You make a whole cosine. But and likewise, if I just wanted the x squared, not the whole cosine of x squared, could use parentheses. But then that's just extra stuff you got to worry about, making sure you get the parentheses every time. So kind of tradition is to write cosine squared. That's when we have a trig function squared. Anyway, I want to show you another one of these where the domain can be kind of tricky. I can find one. Number 3. Three has f of x square root of -6. P of x, I'll put it over here, is square root x squared minus 1. So these have some square roots, and we can't do the square root of a negative and get a real number. So there's obviously going to be some restricted domains on these functions. So before I even worry about the composition, I'm going to worry about the restricted domains of these individual functions. For this one here, what's under the square root has to be bigger than 0. Can't be negative. What's under the square root has to be bigger than or equal to 0. What's under the square root? 5 minus x has to be bigger than or equal to 0. So when I write that down with an inequality, I can solve for x. Just add x on both sides. Five bigger than or equal to x, or if I reverse it around, x has to be less than or equal to 5. So the domain for the f function, 5 to infinity. As long as x is 5 or bigger, did I do something wrong here? Something's not looking.
If it's negative infinity.
Oh yeah, I got this right here. X has to be less than or equal to 5. I said that backwards, definitely wrote it down backwards. So the numbers have to be less than or equal to 5. So it's negative infinity up to 5. X. So as long as the x value is less than or equal to 5, we'd be able to do this calculation. For example, 0. If x were 0, 5 minus 0 is 5, square root of 5. I could do that. It'd be a long decimal number, but I can do it. But if it were 6, 5 minus 6, negative 1, square root of negative 1, can't do that in terms of real numbers. Anyway, for this one, same thing. X squared minus 1 has to be bigger than or equal to 0. What's under the square root has to be bigger than or equal to 0. Now, I believe we did this one last week. And I went through and showed you how to test intervals and stuff, but I'll show you an easier way. If you just look at what we have on the left side, it's a quadratic function, x squared minus 1. So its graph would be a parabola. The graph of y is x squared minus 1. Look like that. You come down here to negative 1. You intersect at negative 1 and positive 1 on the x-axis. And if I want where that function is bigger than or equal to 0, that's going to be above the x-axis. So y values are bigger than 0 for those two branches. In between, it's not. Between negative 1 and positive 1, it's less than 0. So using that shortcut, I could say x has to be less than negative 1 or bigger than positive. So the domain is negative infinity to negative 1. Negative 1 itself is okay. And then we got this other piece, positive 1 to infinity. So the domain is kind of the tricky part with the composition here. Well, those not too bad. No, they don't even want you. They want us to do something besides composition. They want us to figure out f plus g of x. So make a new function by adding the other two individual functions. That just means f of x plus g of x. So just add the individual functions. So that's square root 5 minus x plus x squared minus 1. Ooh. So there's the new function that's the result of adding the individual functions. Now the domain. Now for this, the domain has to be values of x that are in the f and in the g. Because if you want to plug in a number for the x, you need to be able to plug it into the f function and the g, since they're both involved here. So we're looking for the numbers that are in the domain of the f function and in the domain of the g function. One way to figure that out is look at the graphs of these domains on the number line. We got the number line here. The domain for the f function is negative infinity to 5. Negative infinity to 5. So all those numbers are in the domain of f. I just grabbed it, the number one. And then for g, negative infinity, -1. And then 1 to infinity. Now I'm looking for the overlap, because the overlap would be x values that are in the domain of f and in the domain of g. For example, right through here, all of those are in the domain of f and g, because the green overlaps with the orange. So negative infinity up to -1. Negative infinity up to -1. But then after the -1, immediately after the -1, there's not an overlap anymore. Still have the orange, but still part of the domain of f, but it's not part of the domain of g. But then there starts being an overlap again right here, +1, and it overlaps to 5. We got this little part and the 5. Oh, once it reaches 5, beyond that, there's no more overlap between the two. It's in the g, but not the f. So the domain of this new function is the overlap here, negative infinity, -1, union 1, 5. I'm going to jump to part D, where it's got f divided by g. F divided by g. And once it's a new function, that's the result of dividing the two functions. And the reason I want to jump to this part is because there's something extra we need to worry about. Because when you divide, you can't divide by 0. Now, the parts I skipped were subtraction. So the only difference would be a subtraction, but that doesn't affect the domain. Part C had multiplication, so you just multiply the two functions, but that also doesn't affect the domain. But division, we still got to worry about that, but we also have to worry about dividing by 0. Can't divide by 0. The formula is no problem. Just the F formula, square root of 5 minus x, over the G formula. So there's the formula for F divided by G. It's the domain. Now, part of it's still the same, like I said. We still need the x values that are in both of them. But we have to exclude where the denominator is 0. So the extra thing we need to worry about, I'm going to write this down. The domain is negative infinity to -1, union 1 to 5, excluding where the denominator is 0. So it's the same as the previous parts, in the overlap between the two, except I have to throw out where the denominator is 0. So I have to throw out the x values that would solve this equation. They might be able to just look at it and figure it out, but I'll do it out this break. Square both sides, get rid of the square root. X squared minus 1 equals 0 squared, still 0. Add 1 to both sides. X squared is 1. Take the square root principle. Says you get rid of the square by taking the square root, but there's a plus or minus whenever you do that. Plus or minus square root of 1. Plus or minus 1. So x, -1, x, +1. So -1 and +1 are where the denominator would be 0. So I have to exclude those. I have to throw them out. I have to throw out the -1 and the +1. And I can just do that very easily with the symbol. Because negative infinity to -1 with a bracket means up to the -1, including the -1. But I want to exclude the negative one, so I just put a parenthesis instead. Likewise for the positive. Negative infinity to the negative one with a parenthesis. So that means up to the negative one without the negative one itself. Union 1 to 5. Same thing there. I want to exclude the 1, so it gets a parenthesis instead of a bracket. Of course, the 5 isn't affected. It still gets included. It still gets a bracket because that's not where the denominator is 0, so it still leaves out the bracket. Anyway, number 9 is kind of dealing with the idea of composition, but backwards. Number 9 has the function, we call it capital D of x. Cube root of x over 6 plus x. So they give us this function. And what they want us to do is think of this as the result of one function plugged inside of another function. They're saying g of x, this function that they're giving us the formula for, is the result of that composed with g. It's the result of taking one function, plugging it into the other. So what they want us to do in this problem is figure out the g function and figure out the f function. Figure out the g. Yeah. The g function is the one that's being plugged into something else. So how can I think of this as having a function plugged into another function? Now, sometimes there's more than one right answer, but here's how I see it. I've got cube root of this stuff. So you could think of this as this stuff being plugged into the cube root. I could think of it as the x over 6 plus x. So that's what's being plugged into another function. And it's being plugged into the cube root function. Imagine what I circled there is just an x instead of x over 6 plus x. That's just an x. I'd have cube root of x. That's the outer function, cube root of x. There's nothing really to solve. It's just being able to visualize it. That's all there is to it. Sometimes that can be tricky. But again, if you imagine now actually doing the composition, if I took the g, I took all that, plugged it in here, I would indeed get this capital G, get that formula. Again, the kind of trick is, think about it as one function inside the other. If I circle the inner function, that's what gets replaced by just an x for the outer function. Number 11 is the same, but then they take it a step further. Number 11 says, fourth root, h of x is fourth root of 2 plus absolute value of x. They really increase the level of difficulty in this problem. It's kind of the same problem, think of it as composition, but not just one plugged into another. Think of it as one plugged into another, plugged into a third one. They want us to figure out sure my notation agrees. F composed, G composed with H. One function plugged into another, plugged into another. Take out those functions that are being plugged into each other. So the H function is the innermost function. When I look at this, what I see myself is I see fourth root. I see a 2 plus absolute value of x. I see an absolute value of x. There. So the innermost thing here is an absolute value of x. So if that's the innermost function, absolute value of x, that could be my h. So this is my h. So I'm going to replace that with an x to continue on. If I imagine that's just 2 plus x, not an absolute value of x, that's being character, just an x. Then I can think of 2 plus x as being the next function. So this right here is the middle function. Again, my circle there is just an x now. 2 plus just an x. Again, to stop momentarily and show you here, if I took absolute value of x, put it right there, I plug this one into that one, I'd have that 2 plus absolute value of x. And then the final one, the outermost function, if I take all of that I circled in the red and replace that with just an x, I'd have fourth root of x. So that'd be the outermost function, fourth root of x. Again, nothing really to solve. It's just trying to visualize functions inside of functions. But once I decompose it into these individual functions, you can kind of check mentally. I took absolute value of x, put it right there. Now 2 plus absolute value of x. If I took 2 plus absolute value of x, plugged it in there, I wouldn't need to get this original function. Fourth root of 2 plus absolute value of x. Not really hard, but kind of tricky. Another one that's kind of tricky. Again, not really hard, but kind of tricky. Number 10. Number 10 has a table. One, 5, 5, 6, 1, 1, 5, 5, 3, 6, 1, 5, 5, 1, 5, 5, 3, 6, 1. That's some values for the F. I've got this second row. And then I got a third row, G function. 4, 4, 4, 4, 6, 1, 3, 4, 4, 4, 6, 1, 3, 4. 6, 4, 4, 6, 1, 3, 4, 4, 6, 1, 3. So this table is given to you. What this table is giving you is x values across the top, and then function values for the f function in this middle row, and then function values for the g function in the bottom. So what it's saying, for example, is that f of 1 is 1. If I took 1 and plugged it into the f function, I'd get 1. They're not giving me the formula for the f function, but they're just telling me what I would get if I did that. Likewise, if I plugged in 3 into the f function, I'd get 5. That's what that's telling me. And then likewise for the bottom row here, if I took 4 and plugged this into the g function, I'd get 1. That's what it's telling me. Again, they're not giving me the formulas, they're just telling me some of the function values. And then they want me to figure out a bunch of stuff dealing with composition. F of g of 1. F of G of 1. Start on the inside. The X value is 1. And what I need to figure out first is the G value. Function value of G when the X is 1. So when the X is 1, the G is 4. So this right here, G of 1 is 4. Figured that out from the text. That's it. I replace what I circled there with 4. That's the first step. Now the second step, I need to figure out what f of 4 is. So 4 for the x, f 3. And I'm plugging 4 to the f function, I get 3. So the final result, the final answer is 3. Takes 2 steps, a composition like this. But the final result is 3. The answer is 3. B. Same thing, but the other way around. G composed with F. G of F of 1. So you start on the inside. You got the X value of 1. You need to figure out the F value when the X is 1. You need to figure out F of 1. So when the X value is 1, the F function happens to be 1. So when I circled there, F of 1 is 1. G of 1, that's the first step. Now I need to figure out the G value when the X is 1. So when the X is 1, the G is 4. G of 1 is 4. So the final result after those 2 steps is 4. The answer is 4. F of 1. F of 1. Okay, so on the inside, F of 1, you need to figure out the F function value when the X is 1. So when the X is 1, the F function is 1. When that circle there becomes 1. Like I said, my new X value is 1. Figure out the function value. And that is 1. Again, 1. Took 2 steps, had a lot of 1s in there, just like coincidence. Final answer is 1. G of 1. I think that's what they had next. Yeah, G of 1. Just start on the inside here. The X value is 1. What's the G value? X value is 1. What's the G value? 4. What I circled there, the inside is 4. What I circled there became 4. Now I need to figure out G of 4. So the new X value is 4. What's the G value? 1. G of 4 is 1. Coincidence that the previous things were 1. Or E. Now here they were just using, they weren't actually using the composition function. They just were using function notation with one function inside the other. But in the next part, they actually do use the function notation or composition notation, G of F of 3. G of F of 3. Well, what that means is G of F of 3. So I take 3, plug it into the closure function now. Take 3, plug it into the F. The X value is 3. What is the F value? 5. So I circle there becomes 5. F3 is 5. Now my new X value is 5. Plug it into the G function. 5. G function 3. G of 5 is 3. We'll find out in just exactly the same as before, just slightly different notation. F composed with G of 6. F composed with G of 6 means F of G of 6. Take 6, plug it into the G. Take 6, that's the X value. What is the G value? 4. And the X is 6. So this right here becomes 4. New X value is 4. Plug that into the F function. Right. F of 4 is 3. Previous answer was 3, but just a coincidence. All right, this finishes up the 1.3. It finishes up our stuff for the week. As it was, 1.5 was also scheduled to be due next on Monday. And I will postpone that since we haven't got to it yet. We've had a lot of snow days and stuff like that. So 1.5 will be extended. The 1.2 and the 1.3 are due Monday. Anyway, that's all for today. That's all for us this week. Have a great weekend. See you all on Monday.
I was waiting also have class,
Oh,
but
yeah.
like 10 minutes before class, they're like, I'm not coming.
Oh, no.
So-
Okay. Yeah. Well,
I'm
no,
so
no problem.
sorry.
No problem. Yeah. I did not count that. I didn't run through the lost days. I had so much to get through. I jumped straight in. So
Oh, I get
you went down to that.
that. Pick me up. You didn't pick me up. Well, like 10 minutes before class, they're like, you go.
Yeah, no problem. I didn't actually go through the roster this morning, but I knew I had so much to get through. I just jumped straight in. We're not down there, not so much. Like, no problem. Better to be late than not here at all. Yeah. Right, see you.
I think probably they wake up early.